Welcome to the Generative AI Futures, brought to you by Byte Goose AI. We are diving deep today into what can only be described as a monumental shift in the world of temporal AI.
We really are.
We're talking about Chronos-2, a time series foundation model that is, well, it's rewriting the rules of forecasting.
It absolutely is. Forget everything you know about specialized models.
Exactly. Forget models that only work on one type of data. Chronos-2 is being billed as the first truly universal zero-shot forecaster.
And that universal tag is not hyperbole.
This is huge news for anyone who relies on predictive modeling, whether you're in logistics, energy, finance, or, running complex cloud operations.
Anywhere, really.
Our mission today is simple: to provide you with the comprehensive technical analysis of this model, from the deep-seated architectural choices, the underlying mathematics, and the training data strategy, all the way to its groundbreaking empirical performance.
We're aiming for the ultimate shortcut to being well-informed on this.
That's the goal.
And we absolutely must set the scene here by defining the fundamental limitations that Chronos-2 was, engineered to solve.
Please do.
Historically, even the most powerful pre-trained models we've seen, the ones that gave us that first glimpse of zero-shot forecasting, were overwhelmingly limited to univariate forecasting.
Right. So meaning their prediction for a metric depended only on the history of that one metric.
Exactly. And the real world is never, ever univariate. The models were failing to account for the heterogeneity of real systems.
You think about cloud metrics, CPU, memory, disk I/O, they're all deeply interconnected.
They co-evolve, yes. That requires multivariate forecasting. And even more complex, your business outcomes are constantly influenced by external forces, what we call covariates.
It's like promotions influencing retail sales.
Perfect example. Predicting retail sales must account for planned promotions or holiday dates. Prior models just struggled immensely with this heterogeneity problem. Chronos-2 is the first foundation model built from the ground up to solve it.
So the core promise, which is what makes this so revolutionary, is that Chronos-2 is truly zero-shot. It works as is, right out of the box, on completely unseen data sets.
Unseen dynamics, unseen correlations, without any retraining or fine-tuning.
For that specific task or domain, it's just ready to go.
Precisely. And the key to achieving this sort of statistical alchemy is its dramatically enhanced capability for in-context learning, or ICL.
ICL, let's dig into that.
It doesn't need architectural changes. It doesn't need specialized output heads for multivariate versus covariate tasks. It infers the complex relationships and dependencies just by looking at the batch of data you give it at the moment of inference.
So it adapts on the fly.
It adapts its behavior dynamically, and that dynamic, context-aware adaptation is the fundamental shift in the paradigm here.
Okay, so that sets the stage. Let's talk about that paradigm shift then, moving from these old local models to this new universal foundation model.
To really appreciate the scale of this breakthrough, let's quickly establish that traditional landscape. Before foundation models, time series analysis was dominated by two main approaches.
Local and global models.
Right. Local models, your classical workhorses like ARIMA or ETS, were trained one per time series. They were precise for well-behaved data, but they were computationally expensive and couldn't share information.
Which made them pretty useless for short or cold start series, right?
Totally useless. Then you had global models like Deeper, NBeats, or Patch TST. They were more efficient because they shared parameters across a data set of related series.
A necessary step forward.
A necessary step, but they were still constrained to the data set they were trained on. They were, experts in one domain, but they couldn't generalize across domains.
And even as we saw those early pre-trained models emerge, the ones that started enabling zero-shot inference, they still largely had that persistent univariate limitation.
They did.
I mean, the sources point out that models like Times FM 2.5 or Tyrex, if you gave them a multivariate system like 3 interconnected sensors, would just treat each sensor independently.
They'd run 3 separate forecasts, basically. They'd treat the other sensors as, past-only covariates, or just ignore their coevolution completely.
And that structural independence is a fatal flaw when the very thing you need to predict is driven by all those variables peaking at once.
You lose causality. You lose shared shocks. It's a huge problem.
Which brings us back to Chronos-2's universal scope. It's engineered to handle this full spectrum of forecasting tasks in a unified, zero-shot way.
And it really does unify all 3 major task types under one roof.
Let's list them. Number 1, univariate forecasting. The standard single-time series prediction. This is the baseline, and it does this exceptionally well.
Because of the sheer breadth of its pre-training, yes.
Number 2, multivariate forecasting, predicting multiple co-evolving series at the same time. The cloud infrastructure example, CPU, memory, storage, is perfect here.
They share causal dynamics. You have to predict them as a joint system.
And then number 3, which is often the most valuable in practice, covariate-informed forecasting.
This is the big one.
This is when you explicitly condition your forecast on external factors. So staffing needs based on weather or retail demand based on promotions.
And crucially, the model can handle all kinds of covariates. Past only, like old interest rates, known future covariates, like a holiday schedule, and even categorical covariates.
Like product IDs or store locations?
That flexibility is a critical differentiator. You look at Table 1 in the paper, and competitors like Toto 1.0 or Moirai 1.0 had really restricted covariate support, if any.
So Chronos-2 can be dropped into almost any real-world forecasting stack immediately.
Regardless of the data complexity.
Exactly. And the key enabler, as we said, is this in-context learning, or ICL. Let's really unpack what that means for a time series model.
It means the model is flexible at the inference layer, not the training layer. Its architecture is fixed. It infers the relationships and dependencies directly from the context, the batch of data you provide at inference time.
Yeah.
If you tell it, through grouping, that CPU, memory, and I/O are related, it uses its group attention mechanism to infer their shared dynamics right then and there.
So the transformer is the transformer, but its predictive behavior adapts dynamically just based on the inputs and the metadata.
You've got it. The task definition moves out of the architecture and into the data input pipeline.
That's a fascinating shift.
And a crucial side benefit of this ICL approach is something called cross-learning.
Right, I wanted to ask about this.
If you feed it a batch of related univariate series, especially in a cold start scenario where one has a very short history, the model shares information across them.
It borrows strength from the longer, more robust histories.
Precisely, which leads to much more accurate predictions for that cold start series. This transfer of knowledge is a huge practical advantage and is validated in the Chronos Benchmark 2 evaluation, where those short histories are really common.
So it proves that global knowledge can compensate for local data scarcity.
It does. It's a powerful concept.
Okay, that conceptual shift is clear. But the magic has to be in the engineering. Let's peel back the layers and start with how they pre-process the data. The pipeline is a 3-stage system, right?
Right. Stage 1 is all about scaling and tokenization.
So input configuration first. We take historical targets, Y, and covariates, X.
And you concatenate everything historical targets and past covariates into a historical input vector, we'll call it V. The future vector, W, contains the known future covariate values.
And the spots for the future targets are just left empty, essentially.
Filled with missing values, yes.
So for my retail example, Y is sales history, X is promotion dates, and maybe footfall. V holds everything we've seen, and W only holds the future promotion dates I already know about.
You nailed it. And before we even get to scaling, we have to handle the categorical covariates, the non-numeric stuff, like holiday names or product groups.
How does that work?
If the target is univariate, they use target encoding. This maps each category to a number based on its historical relationship with the target. Very informative.
And for multivariate?
For multivariate, they fall back to a simpler ordinal encoding, just assigning a unique integer to each category so you don't bias the encoding toward a single target.
Okay, now let's talk about the math and the robust scaling. I have to challenge this. Why the 2-step process? Isn't standard normalization mean and standard deviation usually enough?
That's a fantastic question, and it's fundamental. Simple standardization assumes your data is, roughly Gaussian.
Normal-ish.
Right. But real-world time series, especially in high volatility areas like finance or retail, are plagued by heavy tails and extreme outliers.
Demand spiking 10x, that sort of thing.
Exactly. And those outliers completely skew the standard deviation. Standard normalization just can't stabilize the variance effectively.
So they needed something more robust.
Which is why they implemented a critical second step, the application of the single-instant transformation.
The inverse hyperbolic sine function.
Yep. It's a technique borrowed from econometrics precisely because it's so robust to these outliers. The function is log-like, so it compresses those extreme values far more effectively than linear standardization. It tames the wild fluctuations.
So the formula check confirms it. First, you normalize the raw value, VLEDD, with the mean and standard deviation.
Correct. Frac B to lie.
And then you apply the inverse hyperbolic sine to that result.
That's right. The full formula is tilde is 1. This single mathematical choice is foundational to its ability to generalize across domains with totally different volatility profiles.
Okay, so once the data is scaled, the model needs contextual signals, what they call meta features. What are we appending here?
Two crucial signals. First, the time index, which they call GGLers. It just encodes the relative position of each time step.
So the model explicitly knows what order things are in.
Yes, which is vital when you're chopping the input into patches.
Yeah.
It provides that non-learned temporal context.
And the second signal.
The second is the mask. This is a simple binary indicator -1 for observed, 0 for missing or future known.
So this is how the model tells the difference between a target it needs to predict and a covariate it can use for the prediction.
Exactly. It's the instruction set for the group attention mechanism later on. And if a value is truly missing from the history, it's replaced with 0, and the mask is also set to 0.
So we have the scaled data, the time index, and the mask. The final substep of stage 1 is patching and embedding.
Right. The long sequence of data with all its meta features gets split into non-overlapping chunks or patches.
And these patches are mapped into a high-dimensional embedding using a residual network.
Correct. And we have to mention the special RegG token here.
Right, the regulator token.
It's inserted right between the patches for the historical context and the patches for the future forecast horizon. It acts as a separator and as an attention sink.
An attention sink, what does that mean?
It helps the model manage information flow. It kind of absorbs some of the attention to prevent noise from the historical context from leaking inappropriately into the future embeddings.
Clever. Okay, so now the prepared patch embeddings enter the model's core. Stage 2.
Stage 2. This is the encoder-only transformer. It's based on the T5 encoder design, which is a really robust architecture.
Why encoder only?
Because time series forecasting is fundamentally about pattern recognition and contextualizing input data. It's not about generating novel sequences token by token like a decoder, like GPT. An encoder-only model is just more efficient for this kind of task.
Makes sense. But the real innovation is how it modifies the attention mechanism, right? It alternates between two types.
Yes. First up is time attention.
And this is just standard self-attention, basically.
It is.
Yeah.
Its job is to aggregate information across patches within a single time series along the temporal axis.
Yeah.
This is how it learns seasonality, trends, autocorrelation.
And they use rotary position embeddings, ROE, instead of T5's original ones.
Right. ROPE, which was popularized by Llama 2, is just much better at encoding positional information over these extremely long sequences that Chronos-2 is trained on.
Okay, so time attention looks along one series, but the mechanism that unlocks ICL, the ability to look sideways at other series, is the custom group attention layer.
This is the secret sauce. Group attention aggregates information across different time series that belong to the same group at a given patch index.
So the group ID is like a set of blinkers.
That's a great way to put it. The group ID tells the attention mechanism exactly which other time series in the batch it's allowed to look at and which ones it has to ignore.
And no positional embeddings here because there's no natural order between time series.
Exactly.
And this group definition is where the model gets its universal title because how you assign the group IDs completely changes the task.
It dictates the model's entire behavior.
So let's run through it again. A single time series in its own group.
That's standard univariate forecasting.
Same group ID for multiple univariate series.
That's cross-learning.
Same group ID for multiple variates of one series, like the cloud metrics.
Now you're doing multivariate forecasting. The model is capturing their shared dynamics.
And the most complex case, covariate-informed forecasting, is when you put the target, the past covariates, and the known future covariates all in the same group.
Exactly. The model is explicitly commanded to share information between the targets and the external factors to derive the forecast. It's all controlled by that simple group ID.
Incredible flexibility. Okay, so after the transformer core does its thing, we move to the final stage, the output.
Stage 3. This is handled by the Quantile head. After the stack of alternating attention layers, the future patch embeddings are passed to a residual block.
And this block produces the direct multi-step quantile forecast.
Correct. The final head.
And Chronos-2 predicts a dense set of 21 quantiles. That's a lot more than usual.
It is. It spans from 0.01 all the way up to 0.99. This gives a much more precise description of the predicted distribution.
Which is critical for risk management.
Absolutely. By including the extremes, 0.01 and 0.99, it provides better coverage of tail risks, those rare but high-impact events. For critical infrastructure or finance, bounding those extremes is way more valuable than just predicting the median.
The model is trained using the standard quantile regression objective, and the loss is only computed on the target
Right.
dimensions.
It ignores the known covariate string loss calculation.
And the final crucial step is inference unscaling. We have to reverse that robust scaling and the Sikli transformation.
We do. We have to get the prediction back into the original units, dollars, CPU percentage, whatever it was.
So you reverse the inverse hyperbolic sign.
The formula for the unscaled quantile forecast is just vatmud plus sigmod. You take the normalized forecast, apply the hyperbolic sign, and then reintroduce the mean and standard deviation.
And that closes the loop. Perfect.
It's an elegant solution.
This architecture is brilliant, but as the sources emphasize for a generalist model, the training data is often even more important than the architecture itself.
Absolutely. The challenge was data scarcity. There just isn't that much high-quality, real-world, multivariate data with clean covariates out there.
So if it was going to learn to be universal, it needed to see every kind of dependency imaginable.
Which is why they had to rely heavily on synthetic data.
And they introduced this idea of multivariatizers. This is the key synthetic data mechanism.
It is. The process starts by sampling individual time series from base univariate generators, AR, ETS, that sort of thing.
But then the multivariatizers step in.
They step in to impose rich, predefined dependencies among these series to create complex multivariate dynamics. They use two main classes to get that diversity.
What were they?
The first class is contemporaneous multivariatizers. These apply transformations at the exact same time step.
So they create instantaneous correlations.
Exactly. The movement in one series is immediately reflected in another, essential for modeling coevolutionary systems.
And the second, more sophisticated class.
Sequential multivariatizers. These are arguably richer because they induce dependencies across time.
Generating things like lead lag effects.
Yes, where one series influences another at a later time step, mimicking delayed causal responses.
And co-integration as well.
Right, where series maintain a long-run equilibrium relationship, even if they diverge in the short term. This required some careful math to make sure the model learned not just short-term noise, but long-term systemic stability.
And it was from this rich pool of synthetic data that they built both the multivariate and the covariate-informed training tasks.
Exactly. This extensive exposure taught the model to recognize a relationship, even when it was only defined by a group ID in the batch. That's what makes it truly universal.
Okay, let's talk about the training process itself. 2 stages, right?
2 stages. In stage 1, pre-training, the model was trained with a max context length of 2048. This is the broad foundational phase.
And then stage 2?
In stage 2, post-training, they extended that context length dramatically to 8192 and increased the number of output patches.
And the benefit of that is capturing those really long-term seasonalities.
Exactly. Annual trends and hourly data, that kind of thing. And it enables true long-horizon forecasts without relying on heuristics that destroy the signal.
And all this culminates in that incredibly flexible zero-shot inference system. Just by changing the group ID and the content of the future inputs, you can switch tasks instantly.
The matrix of possibilities is so simple. For univariate, each item gets a unique group ID. For multivariate, all variates in a series share a group ID.
And for covariate-informed, the targets and all the covariates share a group ID. But the future inputs, W, now contain the known future values for those covariates.
That's the conditionality. The model knows what's coming. And of course, there's the full cross-learning mode where everything in the batch shares one group ID, which is what they used for the general benchmark results.
Okay, so let's talk about those results. The proof is in the performance.
It is. The base model, 120M parameters, was evaluated on 3 major benchmarks: FivBench, Gift-Evil, and Chronos benchmark 2.
And the most comprehensive test was FevBench because it includes multivariate and covariate tasks.
Right. And the results there are, frankly, staggering.
A 90.7% average win rate against all baselines, and a 47.3% skill score relative to seasonal naive. That's almost a 50% improvement.
It's a huge improvement, and what's equally important is the statistical significance. The 95% confidence intervals for Chronos-2's win rate didn't include 50%, and for the skill score, they didn't include 0%.
So they didn't just win, they won by a landslide, statistically speaking.
They shattered the confidence intervals. It's a definitive step forward.
And the success story continued across the other benchmarks, right? On Gift-Evil, which is about high-frequency, long-horizon tasks.
It showed superior performance. We can directly attribute that to the stage 2 long context training. That 8192 context length let it see long seasonal cycles that competitors just missed.
And on Chronos benchmark 2, the one with lots of short histories.
It was consistently the best. This is the direct empirical validation that the cross-learning aspect of ICL is highly effective. It really can compensate for limited data.
Now, foundation models can be computational beasts. What about deployment?
That's another plus. Chronos-2 is highly efficient. The 120M model runs on a single mid-range GPU, an NVIDIA A10G,
And the throughput.
about 300 time series per second. That efficiency is critical for making this practical for real-world enterprise pipelines.
Okay, the overall performance is stellar. But let's dissect where that ICL, the group attention, is providing the biggest returns.
This is where it gets really interesting. On purely univariate tasks, enabling ICL, which means cross-learning, did yield consistent, moderate improvements.
So it stabilizes things, especially on those short context data sets.
Exactly. But here's the surprise.
Go on.
On the multivariate subset of FevBench, enabling ICL provided only modest gains over running the model in its simplified univariate mode.
Wait, really? Isn't that undermining the whole point of group attention for multivariate systems?
It's a critical and counterintuitive finding. The researchers suggest that a sufficiently strong univariate model, especially one with an 8192 context window, can often implicitly capture the dynamics of a larger system.
So it's so good at seeing the patterns in one series that it can infer what the others are doing?
Kind of. It's conceptually tied to things like Taken's embedding theorem. The main takeaway, though, is that Chronos-2's univariate mode is so powerful it still outperforms native multivariate models like Toto 1.0.
Okay, so if ICL is only moderately helpful for multivariate, where does group attention truly shine?
Covariate-informed tasks. This is where it gets really interesting. ICL yields the largest and most substantial gains here. The moment the model moves from ignoring covariates to actively exploiting them, the performance margin is massive.
So this is its killer feature.
This is the key practical differentiator. If your business problem involves external factors, promotions, weather, macroeconomic data, Chronos-2 is built to succeed where others fail because it can condition its forecast on known future events.
Let's make this concrete with those two domain case studies. The energy price forecasting one is a great example.
Right, energy price forecasting,
Yeah.
EPFDE. You're predicting hourly energy prices, and you know the day-ahead forecast for energy load and solar wind generation. Those are your future covariates.
And the univariate forecast is just imprecise.
It's reasonable, but it misses the rapid shifts. It has high uncertainty. The ICL forecast, on the other hand, which uses those covariates, produces predictions that are significantly more accurate.
It tracks the dips and peaks.
Precisely. The consequence of the univariate failure here is real financial risk. The ICL mode mitigates that risk dramatically.
And the retail example, Rossmann sales forecasting, is just as powerful.
It is. The goal is to predict weekly sales, and the covariates are planned promotions and holidays. The univariate forecast is almost flat, just running at an average with high uncertainty.
Because it has no way to explain the spikes.
Exactly. But the ICL forecast leverages that promotion and holiday info. When it sees promotion starts here in the future input, it instantly adjusts its prediction to capture the sales spike.
So that's the difference between running out of stock during a sale or having too many staff on a slow week.
That's it. This is where the advanced engineering translates into clear operational value.
Okay, to finalize our analysis, let's look at the ablation studies, the practical trade-offs.
Right. They examined model size. They trained a smaller version, Chronos-2 small, with just 28M parameters.
And how to do?
Remarkably well. It lagged the base model by only about 1 percentage point on benchmarks like Gift-Evil.
That's a huge operational win. A 28M model is way easier to deploy, maybe even on CPUs.
And it has nearly double the inference speed. It's a great trade-off when speed is the priority.
They also validated the long context, right? The jump from 2048 to 8192.
They did. It yielded consistent gains, especially on Gift-Evil with its high-frequency data. That extra context length really lets the model see those deep, long-term patterns.
And maybe the most philosophical ablation was the Chronos-2 synth variant.
The one trained exclusively on synthetic data.
How did that hold up?
The results are profound. It performed only slightly below the full model and still maintained a strong profile on FevBench.
So what does this all mean?
It means the multivariate synthetic data generation approach is incredibly effective. It taught the model the universal language of time series dynamics without needing a real-world example of every single structure.
So in the future, we might need less real data for pre-training.
It strongly suggests that. The emphasis might shift to synthetic data expertise.
So what's next? Where does this research go from here?
One promising area is multimodal inputs. Right now it handles numbers and categories. The next step is incorporating text or images.
Like using news headlines or product descriptions to inform the forecast.
Exactly. That's the next frontier of contextual learning.
And the other direction.
Retrieval-augmented forecasting. Using dense embeddings of time series to find similar historical examples during inference. This could be a massive boost for small data or cold start scenarios.
Fascinating stuff. Okay, let's try to synthesize all of this.
To synthesize this deep dive, Chronos-2 is a universal zero-shot forecaster. It's enabled by that powerful combination of group attention, sophisticated synthetic data, and the robust scaling with this information.
A combination of architectural innovation and training strategy.
Right. And empirically, it just dramatically closes the performance gap, especially in the practically critical area of covariate-informed forecasting. It sets a new bar for generalization.
My final takeaway is that the architectural shift enabled by the group attention mechanism, the part that lets a single model switch its entire focus just by changing a group ID, is truly revolutionary. This establishes a new standard where one model can adapt to the full spectrum of real-world forecasting
I
challenges.
completely agree.
Now, we spent a lot of time on that two-step robust scaling process, highlighting the importance of the center transformation for handling those heavy tails in messy real-world data.
A critical choice.
It really was. So given how potent that one specialized transformation was, I want to leave you with this provocative thought. We know specialized transformations solve specialized data problems. So how might other, even more specialized, domain-specific data transformations beyond standard log-like functions, maybe ones tailored for extreme skewness or specific patterns in mechanical or financial data, further unlock the predictive power of these massive foundation models, allowing them to excel in niche fields like high-frequency trading or industrial predictive maintenance?
That's a great question to ponder.
Something for you to mull or explore on your own.
Thank you for joining us for this deep dive into Chronos 2.
We'll see you next time.